Okay, so in this lecture, we're going to relate entropy to the second law of thermodynamics. And while there are many different ways in which the second law of thermodynamics can be phrased, the most general is to say that the entropy of the universe must always increase for any process that occurs away from equilibrium. If a process happens to be occurring exactly at equilibrium, then the entropy change of the universe is zero. So the best you can do is that equilibrium process that doesn't increase the entropy of the universe. But anything else that happens is going to have to increase the entropy of the universe. Otherwise, it just can't happen. That's what the second law of thermodynamics says. Okay, so let's see what that looks like in terms of equations. If we say that delta S for the universe describes the entropy change of the universe, that's going to be the sum of the entropy changes for the system and the surroundings. And the second law says that has to be bigger than zero for non-equilibrium and equal for an equilibrium process. So when we're working on the system, we're going to calculate delta S. And when we're trying to do a calculation, we're going to calculate delta S this way, right? So you're going to look at the components of the system and how they change from the initial state, which we're calling the reactants generally here, to the final state, which we're going to call the products, because we're chemists and that's what we think about. But it works for a physical system too. If you're talking about something like condensation, then the reactants would be the gaseous phase, and the products would be the condensed phase, the liquid phase. And incidentally, delta S ought to be negative for that process, right? Because the number of microstates available to the gas are going to be much larger than the number of microstates available to the products. So when you go from gas to liquids, then you're going to get a reduction in the number of microstates, which amounts to a negative delta S. Okay, what about the surroundings? So the effective entropy on the surroundings comes from heat. We know that basically you can transfer heat into the surroundings if you have an exothermic process, or you can extract heat from the surroundings when you have an endothermic process. And so we're going to write it this way. It turns out that the entropy is actually the heat divided by the temperature in a situation like this. So when this process occurs at constant temperature, which is a pretty good approximation for what happens in any system, you assume that the surroundings is large, and so the relatively small amount of heat being exchanged with the surroundings isn't going to change its temperature by very much. Sorry, exchange with the system isn't going to change its temperature very much. So this is a good way to write the equation. And so basically you have temperature in the denominator, and that's because if you think about it this way, remember the entropy is related to the number of microstates. The change of entropy is going to be therefore the change in the number of available microstates. So at a given temperature, when the temperature is high, the entropy is already high. There are already a lot of microstates. So adding a certain amount of heat isn't going to increase that as much as when you start out at a very low temperature and there are hardly any microstates available. Now, if you put in the same amount of heat, you're going to get a big change in the number of available microstates. And so that's going to make the entropy change proportionally a lot larger. So this is the way we're going to represent that. And what's more, we can calculate it because if we're working at constant pressure, as we typically are in chemistry, then the heat in the surroundings is going to be equal to the enthalpy change of the surroundings. And how do we think about the enthalpy change of the surroundings? Well, the heat that came into the surroundings came from the system. So that's just the negative of the enthalpy change for the system, which is what we always are what we were thinking about. We just did a whole unit on that, right? Entropies of reactions and things like that. So this is very useful because we can now say that the entropy change of the surroundings is equal to the negative of the enthalpy change for the system divided by the temperature. So these are all things that are accessible to us, and it turns out we can actually calculate whether or not the entropy of the universe is going up in a given process. All right, so let's stop for a minute and just think about what we've just worked out. If you have delta S, right? So essentially what we're saying is that the entropy of the universe has to increase. So obviously, if both the entropy of the system and the surroundings increase for a process, we're good. Okay, both of those are going in the right direction, so there's no question. It's easy to understand how that process can happen. But what about a case where the entropy of the system goes down? There are plenty of examples of this, right? If you freeze water, right, you're going from a freer state in the liquid with more microstates available to a less free, more restricted state in the solid. So the entropy change for that is going to be negative. That's okay as long as the corresponding entropy change for the surroundings is big enough to compensate for that, right? So it has to be bigger than the negative of the entropy change for the system. And if we think about the freezing of water, yes, the entropy change for the system is less than zero, but remember, freezing is also an exothermic process. And for an exothermic process, the enthalpy change of the system is going to be less than zero, which means this quantity here, the entropy change of the surroundings, is going to be greater than zero. And so that's going to be enough to compensate for it. We know this, at least at 0 degrees Celsius. So that's another way of thinking about this, is that at 25 degrees Celsius, this compensation isn't enough. Okay? The fact that it's exothermic isn't enough to compensate for that loss of entropy, the entropy change being negative. But when you get down to 0 degrees Celsius, now this is able to compensate. And so you actually have the two phases in equilibrium with each other, suggesting that the entropy change of the system is exactly equal to the entropy change and opposite to the entropy change of the surroundings. Okay, so that's why at 0 degrees Celsius, water is in equilibrium between the liquid and solid states. Okay, so what about a case where the entropy of the surroundings is decreasing? And we've seen these cases too, right? An endothermic reaction draws heat out of the surroundings. If that's the case, then that means that is going to be reducing the entropy of the surroundings. And again, that's okay as long as there's a compensating increase in the entropy of the system so that it overwhelms that negative entropy change for the surroundings. So an endothermic reaction, this is just a summary of what I just said. Delta H for the system is going to be greater than zero. So when we put that into this equation, we're going to get an entropy of the surroundings less than zero. But it can still happen if delta S of the system is large enough. The example that I like to use is the dissolving of ammonium nitrate, which is a very endothermic reaction. It's endothermic enough to get ice cold. That's what's in those ice packs that you sometimes use in sports for an injury. You kind of pop it and shake it up and you dissolve the ammonium nitrate in water and it gets really cold really fast. And what's happening is that even though that's a big decrease in the temperature and it's a very endothermic reaction, you're getting a very large increase in entropy because you're taking the solid ammonium nitrate and you're dissolving it into water. So the dispersion of those particles into the solvent creates a sufficient increase in microstates to more than compensate for the loss in entropy of the surroundings. Okay, so hopefully that gives you some sense of how this works in a qualitative way. Let's go on to talk about spontaneity, okay? So the idea of spontaneous processes, because what I really mean here when we're talking about the entropy of the universe is always going to increase, is we're talking about spontaneity, spontaneous processes. A spontaneous process is one that happens, quote, on its own. So in other words, there's no external influence, it's just works that way. Water flows downhill, but it never flows uphill by itself. Heat flows from hot object to a cold object, but never the reverse, not by itself. If you have some sugar and you dissolve it into a solution like your coffee, you see that the sugar will dissolve, but it will never come back and reform into a solid clump by itself. Water freezes at 0 Celsius and boils at 100 degrees Celsius. Okay, those are the spontaneous changes at those temperatures. A strong acid reacts with a strong base to form water and salt. But you never see a cup of salt water all of a sudden turn into strong acid and strong base. It doesn't happen that way. The spontaneous process is the reaction of the acid with the base and not the reverse. If you have two different gases and you release them into the same volume, they're going to mix with each other. And they're never going to spontaneously separate out on their own and repartition. And the last example is if you have a chunk of iron and you expose it to oxygen, it will rust. But you can leave rust out for 1,000,000 years and it's never going to turn back into iron and oxygen. So the idea here is that the universe has some processes that naturally go in the forward direction without any help. Okay? And so all of these processes, the direction that goes by itself is the direction in which the entropy of the universe increases. That's why we observe them happening in that direction. The reverse processes, if they were allowed to happen, would decrease the entropy of the universe, and we can't have that. That's what the second law says is forbidden. That doesn't mean we can't do them. It just means that we have to put energy in from an external source to make them go. So the entropy of the universe still has to go up. It's not going up from the process itself running in reverse, but we're putting in energy from another source. So we're sort of expanding the definition of our system, and the operation of that other energy generating system that we're using to do something like pump water uphill is increasing the entropy of the universe by more than the decrease of water going the wrong way. And another great example is a refrigerator. We can force heat to flow the wrong way. We can get something that is cold to become colder by putting it in a refrigerator. But that refrigerator has to be plugged into something. It's got to be it's got to be drawing energy from a circuit. And the overall system now has to be constructed in such a way that the entropy of the universe goes up. Now, when we consider the energy generation and all the way that you have the compressor or whatever inside the refrigerator, once you take all of that into account, the entropy of the universe is going up again. So this, you can't ever get away from this. Okay, so the last part of this lecture is going to get into the idea of Gibbs free energy. Oops. There we go. So Gibbs free energy is a state function. Okay, so enthalpy is a state function, entropy is a state function. Gibbs free energy is another state function, and it measures the amount of energy from a process that is available to do work. Okay, so if you're doing something like, say, you're burning gasoline inside a combustion engine, you're going to be releasing a certain amount of energy from the burning of that. That's an exothermic process that releases some energy. But not all of that energy is going to be available to do work. In order to figure out how much is available to do work, we have to account for things like the flow of heat into the surroundings and all of the different ways in which the system can lose energy. If there's friction, blah, blah, blah. All of that stuff kind of gets lumped in, and you can calculate the amount of work that you can get out. Okay, the amount of energy from the process that is available to do work, and that is going to be defined as the Gibbs free energy. So let's take a look at this. If delta G, the change in the Gibbs free energy, is less than 0, a process is spontaneous. Okay, so that's the way that the Gibbs free energy change can be really helpful to us. If we are observing a spontaneous process, we know that the change in the Gibbs free energy for that process is less than 0. And the value, whatever the value of that delta G is, so you've got the negative sign, that tells you it's spontaneous. And then how the magnitude of delta G is kind of going to give you the usable energy. That's the amount of energy coming out of the system that could theoretically be used to do work. If you have a battery or something like that, that's just the amount of energy that could push electrons through your phone to light up the screen and make calls and things like that. Okay. So if delta G is greater than 0, now you're talking about a non-spontaneous process. Okay? So when the change in the Gibbs free energy is positive, the process is not going to be spontaneous. And now the magnitude of delta G, right, well, now that we've accounted for the sign, is going to tell you the minimum amount of energy that you're going to have to put into the system to make it go. Right? So this is kind of like the case where you're trying to get a refrigerator to work. You're trying to force heat to flow in the direction that the universe doesn't want it to go. And so you're going to have to put some energy in to make it happen. And this is a way to calculate how much is this is the minimum amount of energy that would have to be supplied for a given process when the change in Gibbs free energy is greater than 0. And notice that these sign conventions stick with the sign conventions we've already been using for things like enthalpy, right? We said when enthalpy is less than 0, negative enthalpy means exothermic. You're getting energy out. So here, when a process is spontaneous, that means there's going to be some usable energy that you can get out of the process. Delta H is greater than 0. That would be endothermic. That means you have to put heat into the system. So here, when you're talking about Gibbs free energy, you're talking about a non-spontaneous process that has to be driven by putting energy in from an external source. Okay, and then the last case is when delta G happens to be equal to 0. In other words, there's no change in either direction for a given reaction. That is the definition of the process being at equilibrium. There's no free energy available, but there's also none required. Okay, so the entropy of the universe isn't changing in a system at equilibrium, and that's another way of saying that delta G equals 0. So I think from this, you're probably getting the sense that the definition of Gibbs free energy is really closely tied to this idea of the second law of thermodynamics. That's absolutely true. In fact, we're going to derive it here for the last part of this lecture. Okay, so the way that we calculate, you're going to use this equation a lot. Okay, you calculate Gibbs free energy for a process as delta G equals the enthalpy change for the process minus the temperature times the entropy change for the process. Okay, and we're going to get lots of practice using that for the rest of this unit. But right now I want to look at where this actually comes from. And it comes directly from the second law. With just a few equation steps, we can see how we get from this formulation of the second law, which says that the entropy of the universe always has to increase. We can get from there to the Gibbs free energy expression. So this is what we already talked about. This is literally what the second law says. And so if we now replace the entropy change for this entropy change for the surroundings with the definition that we said before, that's given by the enthalpy change of the system divided by the temperature of the surroundings. Okay, so this is just a simple replacement that we already talked about on the first slide. Okay, nothing new. And now we're going to multiply through by temperature. Okay, so now everything's just been multiplied by temperature. So now we just have the enthalpy change by itself. We have T delta S for the system. So we're already getting pretty close to what we have up here. We just kind of have to figure out the rest of this. Okay, and now if we flip the sign on everything, that makes this side negative T delta S of the universe. We're going to have delta H for the system. And you're going to have negative T delta S for the system. And of course, when you flip the sign, this becomes a less than from a greater than. So this now says the second law. It says basically, remember where we started. We started from the second law being satisfied. It says that if this quantity on the right-hand side of this equation is less than 0, then a process will be spontaneous. Okay? So the Gibbs free energy is a direct measure of the spontaneity of a process. So those things that are allowed by the second law that happen automatically in the universe without any external influence are the things that increase the entropy of the universe. And those are also the things, by this little deduction here, for which delta G will be less than 0 if we define delta G to be this quantity right here. So that's the Gibbs free energy change. All right, so now you should have some problems to work on. They're going to be from the first 3 topics on the AP Central website. So go on there and you've got a few problems. You need to work through them kind of quickly because they're technically due at the end of your class period. Good luck.